Now, uniqueness of interpolating polynomial. Uniqueness of interpolating polynomial. The statement is the interpolating polynomial. The interpolating polynomial obtained in two different ways. Obtained in two different ways. May be different in form. Different. Maybe different in form. Means two different forms may be there, but they are identical. But they are same. They are identical. Identical otherwise. And depending on, so we are applying so many methods to find interpolating polynomial. You will get polynomials, but they looks different. But if I simplify, you will get same unique interpolating polynomial. That is the answer. Okay. So depending on its form, the polynomial is called either Lagrange interpolating polynomial, or it is also called as Newton's divide difference. Newton divided difference interpolating polynomial. Okay, so here we are learning only two cases. One is Lagrange's and Newton's divide difference interpolating polynomial. They looks different, but if I simplify them, you will get unique interpolating polynomial. Okay. Now, first let us see linear interpolation. What you know what is meant by linear interpolation? Means nothing but what? Getting approximate polynomial. Linear interpolation means first degree polynomial. So here we want to determine a polynomial of the form. What is the form here? P of x, that is approximating interpolating polynomial, equal to a1x plus a0, equation 1, where the or a0 and a1 are arbitrary constants. We have to find these constants which satisfies the interpolating conditions. Which satisfies the interpolating conditions. What are the conditions? You know what are the conditions? P of x naught equal to f of x naught, and another one is what? P of x1 equal to f of x1. These are interpolating conditions. Why I am taking only 2 points, x0 and x1? Because two arbitrary constants a0 and a1 have to be determined. So two conditions are required. Therefore we have what is the first one? At x equal to x0, equation 1 implies, that is P of x0 equal to a1 x0 plus a0. At x equal to x1, equation 1 implies P of x1 equal to a1 x1 plus a naught. And what is this value? P of x naught is what? F of x naught, and this is f of x1. Okay, therefore what we have equations now. Therefore finally we have what is the first approximating polynomial? P of x equal to a1x plus a naught. First equation. And second equation, f of x naught equal to a1 x naught plus a naught. And another equation, f of x1 equal to a1 x1 plus a naught. Okay, now eliminating a naught and a1 from the above equations. We have, now I am using the determinant model. We have, what is that? From the first equation, the first quotients of a naught and a1. From the second equation, x naught 1. From the third equation, x1 1. This determinant must be equal to 0. Solution of the system of equations, like, okay, this is, take this as equation 2, and the linear interpolation is shown in the graph as just 1 minute. Shown in the graph as, see, let me draw the graph. This is x-axis and this is y-axis. Okay, and what is my graph here? This is my graph, for example. Okay, and let me take this point as x0 and another point as x1. Okay, and at x0, what is the value? This is x0, and this point is what point? x0 comma f0 value, right? And similarly, this is a point, this is x1, and this point is what? x1 comma f1 value. And what is this curve? This curve is y equal to f of x curve. Now let me join these two to get the straight line, linear interpolation. This is linear interpolation. What is this? Is y equal to what? Not f of x. What is this? P of x. At this endpoint, the curve meets. The function values are same, but now this part of the curve is not matching with straight line, right? This part of the curve not matching with the straight line. This is called error between f of x and p of x. Okay, this is a linear interpolation graph. Now Lagrange interpolation. See, first let me apply Lagrange interpolation for linear form, then quadratic form. Okay, now you have to write the from the beginning. Okay, let me write. If you want to explain, consider a linear polynomial. Same, I am writing again. P of x equal to a1x plus a naught, equation 1. Okay, where a naught and a1 are arbitrary constants, which satisfies the interpolating conditions. What are the conditions? P of x naught equal to f naught or f of x naught, P of x1 equal to f of x1. Okay, then 1 gives, what is the first one? P of x naught is nothing but a1 x naught plus a naught. This is nothing but f of x naught and the p of x1 is a1 x1 plus a0. This is f of x1. Okay, take this as 2 and take this as 3. From 1 to 3, from 1 to 3, eliminating the arbitrary constants, eliminating the arbitrary constants, eliminating the arbitrary constants, a0, a1, we have next line the determinant. What is the determinant? In the first expression p of x, x1, and the second expression f of x0, x0 1, third equation f of x1, x1 1, this equals to 0, this equals to 0. Now what we are doing to get Lagrange's interpolation formula, expand, now expand this determinant, expand this determinant using first column, using first column. Then first column means what is the expansion? This is p of x into x0 minus x1, correct, minus x into this one was f of x0 minus f of x1 plus 1 into f of x0 into x1 minus x0 into f of x1, isn't it? Using first column now, sorry, this is first row, first column I have to expand up to here, same, up to here first term is over, second one minus f of x0, this one goes, therefore x minus x1 plus f of x1 using first column. So this first column, first row gone, x minus x0 equal to 0, right? From this what I'm getting, p of x equal to x minus x1 into f of x0, right, minus x minus x0 into f of x1, right? Okay, this is multiplied by what? x0 minus x1. So from this what is p of x equal to? P of x equal to x minus x1 by x0 minus x1 into f of x0 plus, right? Okay, next one, x minus x0 by x1 minus x0 into f of x1, isn't it, right? Okay, this is x0 minus x1, this is as usual, right? No change here. Here minus is common in denominator, so taken to plus. This is our next formula. Remember this, this is equation 4, equation 4, which can be written as p of x equal to L0 x into f of x0 plus L1 x into f of x1. This is equation number 5. Both are same. Okay, either this is called Lagrange's interpolation formula, Lagrange interpolation formula, or what is this? This is Lagrange interpolation formula, Lagrange interpolation formula. Both are same. Where what is L0 of x? L0 stands for x minus x1 by, replace x by x0 in denominator. This L0, and L1 x is what? X minus x0 by, replace x by x1 here, are called Lagrange fundamental polynomials, Lagrange fundamental polynomials. Okay, and we noticed that what is the properties? What noticed that one property is what? L0 x into first one, L0 x plus L1 x. What is this? Is clearly x minus x1 by x0 minus x1 plus x minus x0 by x1 minus x0. If I take its denominators as same, you will get 1 value, you will get 1. And second observation is what? L naught of, if I replace x naught, x by x naught, then you will get 1. And L naught of x1 value 0. Next one, L naught of L1 of x naught is 0. Next one, L1 of x1 is 1. Okay, these are the properties of Lagrange's fundamental polynomials. Remember these two. And in general, one can write this 1 0 1 0 all together. These conditions can be written as Li of xj. Li of xj, notation is delta ij. Its value 1 for I equal to j, and 0 for I not equals to j. This is, these two combinedly can be taken as like this, Li of xj. And to explain this concept, remember, this is the data x versus function of x. X versus function of x. How many data points I'm considering? Only 2 data points, and the corresponding function values here, x0 x1 and x1 f of x1. Then how to write Lagrange's polynomial p of x equal to, first actually the difference is x minus x0 x minus x1. For the first term, write the difference x minus x1, not, and in this expression replace x by x0, same expression but x replaced by x0, and write the function value at x0. This is the first term, plus. And second one, write remove x minus x1, write x minus x0 difference by replace x by x1 now, and the function value at second data point. This is Lagrange's interpolation polynomial. This is Lagrange's interpolation polynomial. Okay, and coming to the properties, what is this I'm giving here? This is x0 point and this is x1 point. And what is our Lagrange's polynomial here? L0 of x here and L1 of x here. Okay, and here what are the properties? L0 of x0 is 1. L0 of, what is L0 at this point? x1 0. And here L0, L1 of x0 is not here, therefore 0. And L1 of x1 is 1. Okay, just for the idea, these are the properties. Okay, and clearly L0 x and L1 x are first degree polynomials, right? Are first degree polynomials. So this is Lagrange's interpolation formula of first degree, nothing but linear interpolation. This is about Lagrange's. Now coming to another formula, another interpolation, iterated linear interpolation. This is another one. Okay, and from this, what how to, again you have to write, derive up to equation 4. Okay, same process, just I'm mentioning same process up to equation 1 2 3 4, up to equation 4, I think, right? Just let me see, 1 2 3 4, this is 5 6, up to equation 5 same, up to equation 5 same. Now here, what is the Lagrange's interpolation polynomial? Lagrange interpolation polynomial is, what is that polynomial? P of x equal to, again I am writing x minus x1 by x0 minus x1 multiplied by f of x0 plus x minus x0 by x1 minus x0 into f of x1. Okay, and this, rewrite this. Okay, we can write this equation as, okay, this is equation 5, I think, right? Equation as P of x equal to, I'm taking this x1 minus x0 common, then what is this becomes x1 minus x f of x naught, taking minus common, and x naught minus x f of x1. Just same polynomial, but just I'm taking manipulating the terms. 1 by x1 minus x naught, and this can be written as determinant of, what is this? I can write this as f of x naught, and here I will write x1 minus x naught minus x f of x1 in determinant format, right? This into this minus this into this, right? Okay, so this can be written as, okay, I will write one more step, x1 minus x naught, and notation for this f of x naught is taken as I naught x naught minus x, and this is taken as I1x, this is x1 minus x, this is x1 minus x. This implies p of x is now written as I01 of x, I01 of x. What is I01 of x? Where I01 of x is this determinant. What is that? 1 by x1 minus x naught, I naught x, x naught minus x, I1x, x1 minus x, right? Where I naught x is nothing but what? F of x naught. I1x is nothing but what? F of x1. F of x1. Okay, and this I naught x, I1x are two independent 0-degree interpolating polynomials to f of x. Okay, and what we the observation is what? I01 of x naught. Remember this. This is iterative polynomial, and what is this? You have to remember this, and these two also. I01 x naught is what? F of x naught. F of x naught. And I01 of x1 is what? F of x1, isn't it? In this determinant, if I put x naught, this is x naught minus x naught. Okay, this part 0, and you will get only this I naught. Okay, and this x1 minus x naught gets cancelled. After simplification of determinant, you will get these two. And the main point is now, what do you write? The equation 4.16, this is number, you can take 6 or no, the equation 6, okay, is called Itkens or iterated linear interpolating polynomial. Itkens or iterated linear interpolating polynomial. This is one more method. Now, Newton's divided difference interpolation. Newton's divided difference interpolation, the third one. Okay, and what is the concept here? We have you write up to equation the determinant, right, up to the determinant as in Lagrange, as in linear interpolation. Okay, don't write this one in examination, you have to derive this. Okay, write up to determinant as in linear interpolation. What is the determinant? Okay, we have, what is the determinant? P of x, x1, next one f of x naught, x naught 1, f of x1, x1 1 equal to 0, right? This is linear interpolation. From this one only we derived Lagrange's interpolation as well as iterated linear interpolation. Now using the same determinant, we are deriving Newton's divide difference formula. How it is? See, expand this determinant, expand this determinant, expand this determinant in terms of the first row, in terms of the first row, that is about the first row, in terms of the first row. Then what is this one? First row means the expansion of determinant using first row, using this first row, p of x into what is this, x naught minus x1 minus x into what is this, f of x naught minus f of x1, right, plus 1 into x1 into f of x naught minus x naught into f of x1 equal to 0, equal to 0. The next step is write this expression for p of x. P of x into x naught minus x1 is equal to what? You are getting what? X into this x minus x naught, you keep that one as it is. Okay, let me take these terms onto that side. X into f of x naught, this minus term becomes plus onto that side, and minus x into f of x1 plus x1 into f of x naught minus, okay, wait, this term plus term goes to minus, so minus x1 into f of x naught, and this minus into minus plus x naught into f of x1 equal to 0. Okay, so this implies what I'm getting, this is p of x into x naught minus x1 equal to, okay, now f of this one is common, f of x naught common in these two terms, then I am getting x minus x1, otherwise you take like this, yeah, both are same. Okay, x minus x1 into f of x naught, next one minus next these two minus common, x minus x naught into f of x1, x minus x naught into f of x naught, right? Okay, then what I'm getting, this 1 into, right, okay, minus x into, right, so this value is by this one, by this one, then I have to get cancel these terms, f of x naught plus, okay, now see, write this one as p of x into x minus x naught is equal to, in the first term this is x minus x1, let us add and subtract x naught, add and subtract x naught, f of x naught, and this term as usual, x minus x naught into f of x1, so this is equal to, let us club these two terms first, these two terms, so x minus x naught into f of x naught, and remaining plus x naught minus x1 into f of x naught minus x minus x naught into f of x1. So I can write this term first, x naught minus x1, x naught minus x1 into f of x naught, right, and in these two terms the common is what, x minus x naught is common, and this becomes what, f of x naught minus f of x1, right, and what is this value, p of x into, and what is this, x naught minus x1, this is x naught minus x1, right? Okay, so this implies what is p of x is now x naught minus x1 into f of x naught by x naught minus x1 plus x minus x naught into f of x naught minus f of x1 by x naught minus x1 by x naught minus x1. So finally what I'm getting, p of x equal to, these two gets cancelled, f of x naught, right, plus x minus x naught into this f of x1 minus f of x naught by x1 minus x naught by x1 minus x naught. This can be written as this p of x equal to f of x naught plus x minus x naught into this bracket term can be written as f of x naught x1. F of x naught x1 is called Newton's divided difference interpolation. Divided difference interpolation formula. Interpolation formula for what? P of x. For P of x. And what is the notation here? F of x naught comma x1, where f, this closed bracket, not open bracket, x naught comma x1, this is taken as f of x1 minus f of x naught by x1 minus x naught is called, this one is called, what is this one? Differences in function by differences in x values is called first divide difference. First divided difference. First divided difference of f of x relative to of f of x relative to x naught and x1, relative to x naught and x1, right? Therefore the difference formula, now I can write what is this one. Therefore what is P of x equal to f of x naught plus x minus x naught into f of x naught x1 can be written as, from this I can write this f of x naught x1. F of x naught x1 is what? P of x minus f of x naught by x minus x naught. X minus x naught. And either this equation or previous equation, that's better. Okay, remember the previous one, what is that? Newton's divided difference formula. Finally you write Newton's divided difference interpolation formula is exactly this one. Okay, let me write once again. What is that? P of x is equal to f of x naught plus x minus x naught into the first divided difference. Remember this, where what is this? F of x naught x1, first divide difference is, what is this notation? F of x1 minus f of x naught by x1 minus x naught. X1 minus x naught. Now what is the error in this formula? Truncation error bounds in divide difference formula or Lagrange's formula. Let us see. What is this? The polynomial. What is the interpolating polynomial? P of x coincides with the function f of x at what points? Clearly you know, at x0 and x1. That is, what is the interpolating conditions? P of x0 equal to f of x0 and P of x1 equal to f of x1. So at these points x0 and x1 there is no error. P of x is what? Approximate polynomial. F of x is what? Original function. Okay, and P of x deviates means difference, deviates at all other points with the f of x. That means P of x is not equal to f of x or at all other point. This deviation is called the truncation error. This deviation is called the truncation error. Okay, for your idea I will show this one. Previously we have drawn one graph. What is that? This is the function y equal to f of x, original curve. and x0 I have taken here, and x1 I have taken here. This is the point. What is the point? x0 comma f0, and this is the point x1 comma f1, x1 comma f1. Then join these two curves. Linear interpolation means straight line. This is what is the curve? Y equal to p of x. So at x0 and x1, both are the curve and the line coincides each other. So p of x coincides f of x at what points? x0 and x1. And the remaining, what is this one? This is the original curve. This is the original curve, and this is the approximate curve. So there is a lot of deviation between p of x and f of x at all other points. At all other points, that is called truncation error. That is called truncation error. And it may be written as, truncation error. I am showing the notation this as e1 of f at other points x equal to, what is that? Exact curve minus approximate curve. Exact curve is f of x, approximate curve is p of x. This is equation 1. Okay, now we have to derive expression for e1x. We have to derive expression. That means what is the value, what is the bound expression for e1 of fx. For what? For all other points. X belongs to what? x0 and x1. X belongs to what? x0 and x1. For this, we use the Rolle's theorem condition. For this, we use the Rolle's theorem. Your analysis, okay, topic. Rolle's theorem given by, what is the statement? Rolle's theorem statement. It is given by, if g of x, let me consider another function, some definition, is a continuous function, on some interval closed a comma b, and the differentiable on open a comma b, and what is the condition? G of a equal to 0 and g of b is also 0. One can write, if g of x is the first condition continuous, and second condition differentiable, and the third condition g of a equal to g of b equal to 0, then there exists one point, at least one point, what is that? Xi belongs to open AB. Okay, such that what? G dash xi equals to 0. Okay, we use this Rolle's theorem condition to derive the error bound. Let us see how it is implemented. Okay, now what is that? We have at x equal to x0, even of f x0, what is the value? Since at the x0 point and x1 point, the approximate polynomial, that is what? Since f of x0 is nothing but what? P of x0, so there is no error. Similarly, at x equal to x1 also, we have even of f of x1. This is also 0. Why? Because f of x1 equal to p of x1. At all other points, they are not equal. Okay, right? Then therefore, if x belongs to in between x0 and x1, then x belongs to in between x0 and x1, then for this x value, for this x in between x0 and x, we define a function. G of t as, okay, the function g of t as, what is the function g of t? G of t equal to exact polynomial minus approximate polynomial, g of t minus p of t g of t minus p of t minus f of x minus p of x, f of x minus p of x multiplied by t minus x naught, t minus x1 whole by x minus x naught, x minus x1, x minus x1. This is 2, equation 2. Now how they consider this function? This is called barrier function. Generally, to prove any truncation error method, they assume some polynomial, and how this polynomial is assumed? We assume this polynomial so that it satisfies the conditions of Rolle's theorem. Okay, so they assumed this polynomial. Now clearly what is g of t? G of t is equal to 0 at what point? See, at if I put t equal to x naught, t equal to x naught, f of x naught, p of x naught, both are same, so this part 0, and here also f of x naught, p of x naught 0. So entirely what? G of t at a t equal to t naught, t equal to x naught, and similarly t equal to x1 also it is 0. And one more point, if I take t equal to x also, here t equal to x also, g of t is 0. G of t is 0. You can observe clearly by substituting t equal to x naught, t equal to x1, and t equal to x in the expression 2. G of t will be 0. Therefore, and what are the endpoints here? Endpoints here clearly. Therefore, let me write g of x naught equal to 0, g of x1 equal to 0, g of x1 equal to 0, g of x1 equal to 0, and what is this? G of t is continuous and differentiable, continuous and differentiable, right? So g of t satisfies, therefore g of t satisfies conditions of Rolle's theorem. G of t satisfies conditions of Rolle's theorem, conditions of Rolle's theorem. Therefore conditions of Rolle's theorem, you can write this one like this: conditions of Rolle's theorem on the intervals. There are two intervals here. What are those intervals? On the intervals, one is x0 comma t, and another one is t comma x1 separately, because both are zeros. And one more is what here? Let me write here. G of t is also what? 0. G of t is also 0 separately. Then we get, what is that? G dash derivative at xi. Let me take xi1. G dash xi1 equal to 0, where xi1 belongs to what? Xi1 belongs to what? x0 comma t. And one more is what? G dash of xi2, again Rolle's theorem, where xi2 belongs to what? Xi2 belongs to what? T comma x1, t comma x1. Okay, this is by using the conclusion of Rolle's theorem. Then now what is the thing here? Another point is, now what is g dash t? G dash t means derivative of g of t with respect to t, with respect to t. G dash t also satisfies, g dash t also satisfies the conditions of Rolle's theorem, conditions of Rolle's theorem. Therefore applying Rolle's theorem, for, now instead of g of t, now let us apply Rolle's theorem for g dash t on the interval. What is interval here? On the interval, let us take the interval as these two roots, xi1 and xi2. We get, what is the finally, now what is the function? G dash t. So g double dash xi equals to 0, where xi belongs to what? Open xi1 comma xi2. We are applying Rolle's theorem on what? G dash t. So conclusion is what? G double dash xi equals to 0. Okay, or what is this becomes? Xi belongs to, or one can write xi belongs to x0 comma x1, because xi1 and xi2 lies between what, x0 and x1. So xi belongs to x0 and x1. Now differentiating to get double derivative, differentiating to with respect to t twicely from g of t expression. Okay, we get g double dash t is equal to f double dash t, right, minus 2 into f of x minus p of x. X terms are constants when I take differentiation with respect to t. Okay, and this becomes x minus x naught into x minus x1. This is equation 3. Now what is that? G double dash xi equals to 0. Now setting g double dash xi equals to 0 and solving equation 3 for f of x. For f of x, we get in equation 3 substitute g double dash in place of t, substitute xi value and put g double dash xi equals to 0 and solve this equation for what, f of x. We get f of x equal to p of x plus 1 by 2 x minus x naught x minus x1 into f double dash xi. This is important equation, remember this, fourth equation 4. And therefore this implies what, f of x minus p of x is equal to what, 1 by 2 x minus x naught x minus x1 into f double dash xi, right? And what is this expression? This is nothing but what, e error, truncation error, e of f comma x is equal to what now, 1 by 2 x minus x naught x minus x1 multiplied by f double prime xi. This is equation 5. This is the truncation error. Now to determine what is the bound, what is this? If we can determine a bound for f double dash x in x0 comma x1, that is what is the bound? If I take modulus of f double dash x is less than or equal to some constant value, take this as m2, where x belongs to what, x0 x1, then what is the error? E1 f x, okay, modulus is equal to what is the expression, 1 by 2 x minus x naught x minus x1 f double dash x mod xi, f double dash xi mod, right? Then this is less than or equal to 1 by 2 maximum over x naught less than or equal to x less than or equal to x1 modulus of x minus x naught modulus of x minus x1 f double dash xi. This is mod. Then this is less than or equal to 1 by 2 maximum of x naught less than or equal to x less than or equal to x1 mod x minus x naught into x minus x1 and what is this, f double dash xi mod m2. This is equation number 5. This is the error bound, e1 of f x, okay. Now to simplify this, to get in terms of h, the maximum value of now we have to find what is the maximum value of this expression. Okay, the maximum value of mod x minus x naught x minus x1 occurs at x equal to midpoint x naught plus x1 by 2, x naught plus x1 by 2, then equation 5 becomes, what it becomes now, it is equation becomes error, truncation error is equal to, this is equation 5 implies less than or equal to, okay, this is 1 by 2 and this is 1 by 2, so this is, and one can write, if I substitute x equal to x naught plus x1 by 2, and I'm getting this value finally after simplification. Let me write directly after simplification, 1 by 8 x1 minus x naught, there is no x term because x is replaced by x naught plus x1 by 2 whole square of m2, equation 6. Now to simplify that expression, error expression, assume the tabular points x naught, x1 and so on xn are equally spaced with the common difference h, that is meaning what, x1 minus x naught is h, x2 minus x1 is h, right? So one can write x2 equal to x1 plus h, and what is this, x1 equal to x naught plus h, and if I substitute x1 value here, you will get x naught plus 2h, x2 equal to, and so on. Let me write x3 equal to x naught plus 3h. So in general, for equispaced data, we have xi equal to x naught plus ih, so xi, what is x naught, our starting point a plus ih, I is from where, 0 1 2 and so on up to n, and what is h becomes obviously h equal to last point, the length of the interval, b minus a by n, therefore the modulus of e1 of f x becomes what, less than or equal to, what is this value, 1 by 8 x1 minus x naught whole square m2, this becomes what, this is less than or equal to 1 by 8 h square, h square m2, 1 by 8 h square m2. If for example, therefore maximum absolute error, that means error cannot exceed this value, maximum absolute means positive, maximum absolute truncation error, using, what is this, is completely linear interpolation, using linear interpolation polynomial, using linear interpolating polynomial. What is that, p of x is less than a given error tolerance, epsilon, which is positive value, then what is this expression gives, this is what, mod e1 of f x, then what I am having, this mod e1 of f x is less than or equal to epsilon, that implies what, this h square by 8, okay, and this maximum of, what is m2 value, m2 means what, f double dash x, and over what interval, x naught less than or equal to x less than or equal to xn, that means total interval AB, it must be less than or equal to epsilon. Okay, and always you remember this is important. This is the maximum error, it cannot exceed h square by 8 m2. Okay, this is truncation error bound for linear interpolating polynomial.